Hello everyone, how are you? In the last session, we have learned about the Faraday's law and the Lenz law. In today's session, we are going to do a lot of examples on the Lenz law, and then we will move toward the Faraday's law examples, because we should first know how to find the direction, because magnitude calculation everyone knows, but the important thing is the calculation of direction. Clear? So let us do that. So let us just start with the example. I am just giving a new page so that it will be separate for you. Illustrations, just give a heading, illustrations on Lenz law. You should be very much familiar how to calculate the direction. Okay, illustrations on Lenz law, correct? So let us talk about this. This is my loop, okay, and suppose here the magnetic field is decreasing. Okay, so first thing is that magnetic field is decreasing, so that is the reason, correct, because then the flux will decrease. That is a simple thing. So it is decreasing in outward direction, so what it will try to do, in according to the Lenz law, it will try to increase the magnetic field, correct? So we have to increase the magnetic field. So how to increase? We have to increase in the outward direction, because outward direction is decreasing, so we have to increase. So we have to increase in outward direction only. Keep your thumb in the outward, curl your finger, it is in this direction, so current will like this, correct? Simple. This is how you can tell. Clear? Clear here? Okay, so let us take another example. I have a lot of examples, okay, just try to solve it. Suppose I is increasing, and suppose there is a loop is there, I is increasing and there is a loop. You have to tell me what is the direction of current induced in this. Okay, you have to tell me what is the direction of current induced in this. I'm not asking anything, just you tell me the direction. Just fast put the directions by yourself. This is very easy only. Okay, this is A radius, this is B radius. A is very much smaller than. Okay, yeah, so what is the direction in this? So first, but due to this wire, the magnetic field will be inside, correct? Okay, so the magnetic field is inside, that is sure. Now if the magnetic field is inside, the current is increasing, so magnetic field will increase, correct? So flux will increase, so it will try to induce a current in such a way that the magnetic field will decrease, or this, because that is the only reason. So we have to decrease the magnetic field. If the magnetic field inside is increasing, we have to decrease, so we have to keep the magnetic field outside, and curl your finger. So what is the direction you are getting? You are getting this direction, correct? Now similarly here, in this direction the current is decreasing. Current is decreasing means the magnetic, if you see, the magnetic field is outward direction. First of all the magnetic field is outward direction, correct? Okay, now if you see, the current is increasing or decreasing, so magnetic field will decrease. If the magnetic field will decrease, the flux will decrease, so it will try to induce a current in such a way that it will increase that magnetic field or magnetic flux. So it will increase the magnetic field or magnetic flux in the same direction, because we have to increase, so it will be like this. So current is in this direction. Similarly here, see, what is the magnetic current is increasing, so magnetic field at the center will be what? Increase or decrease? First of all, what is the direction? The direction will be outward. Okay, so first of all the direction is outward. Okay, first of all the direction is outward. That is very much clear to you. Now current is increasing, correct? As current is increasing, so obviously the magnetic field is increasing, but it is increasing in which direction? It is increasing in outward direction, correct? It will try to induce a current in which the magnetic field will decrease, so it will put the magnetic field inside and curl in this direction, so the current will be in this direction, correct? So this is how you can find out the direction. Let us take some more examples. Okay, I have a lot of examples. Okay, you have to try to solve it. I have a lot of examples. Suppose this is my circular coil and there is a one loop is placed here, and the current in this is I. Okay, and suppose this I is increasing. Okay, you have to tell me the direction in this. Okay, or it is better to draw like this. Correct, you have to tell me the direction of current in this. Okay, next example. Okay, first you tell me. Next example. Tell fast. Tell fast. See, if you see the first case, in this case, what is the first of all, the current is like this. Okay, sorry, the current is like this. So the magnetic field is inside. So can you draw the magnetic field lines due to this? If you draw the magnetic field lines due to this, it will be something like this. Correct? Okay. So in the loop, in this loop, the magnetic field is outward like this. Are you getting my point? The magnetic field is like this. Correct? Current is increasing, so magnetic field is increasing in this direction. So it will try to decrease the magnetic field, correct, in this direction, in the opposite direction, so the current will induce in this such a manner. Okay, this is the direction of I induced. Getting the point? It is very easy. Now you see here, I have given us some different case. Now you see, when this bar magnet will come closer, when this bar magnet will come closer to this loop, what this loop will say? What this loop will say? Current carrying, suppose this is a loop and this bar magnet is coming closer to it. What this loop will say? The loop will say, please don't come toward me. Please don't come toward me. Or you can see the magnetic field lines like this, correct? It is something like this. So when this loop is coming closer to the when this bar magnet is coming closer to this, it will say the magnetic field is increasing. So it will try to decrease the magnetic field. So you have to keep his thumb like this and then curl like this. But let us forget this. Suppose this bar magnet is coming closer to this loop. What this loop will say? Please don't come toward me. So what it will do? It will make a north pole in this side, south pole this side, so that it will repel this and won't come closer to it. And if it is a north pole, then the current will be anti-clockwise. Anti-clockwise. And if it is south pole, here the current will be clockwise. Simple. No need to find this direction, nothing, no need. Just you see here. Similarly here also, this is coming closer to it. So what it will say? Please don't come closer to it. So what it will do? It will build north here, south here. If north here is and south is here, so what is the direction of current in this case? It is anti-clockwise. And what is the direction of this? It is clockwise. Simple. It is clear or not? Are you getting the point? What I am trying to say? Are you getting the point? What I am trying to say? Clear? So this is how you can find the direction. Let us take some more examples. You have to be very much confident while finding the directions. Okay. So suppose this is a loop and we have a wire inside this. This is the wire. It is going like this. Okay. This is my wire. And the current I is increasing. I want to know what is the direction of current. What is the direction of current? First of all, check whether the magnetic flux is there or not. See, if you see according to this, what is the direction of magnetic field? The magnetic field is like this, correct? We know about the magnetic field due to the current carrying wire. This is like this. And what is area vector? Area vector is like this. So the magnetic field is in this plane and the area vector is like this. So the angle between the magnetic field and the area vector is 90 degree. Angle is 90 degrees. So the flux is 0. In this case, if you are not able to understand, the flux is 0 here. So what is current? Current is 0 here. There is no current induced. Current will be 0. Okay. I am just given this question to test your mind whether you are seeing, whether you are solving logically or you are just doing it. Are you getting the point? Okay. Clear? Okay, let's take some more example. Suppose there is a loop which is entering, then this is the second stage and then this is the third stage. It is coming out. Okay, there are the three stages are there for this loop. First stage, it is entering. Okay, second stage, it is completely inside, and third stage, it is coming outside. You have to tell me the direction of current. Okay, this is magnetic field which is constant. Obviously it is constant, it is not changing. You have to tell me the direction of current. Okay, there is you have to tell me the direction of current. First, try to analyze how what is the reason that magnetic flux is getting changed and how to find out the direction. See, if you try to see the things very properly, you will see that as it is going inside, what is changing here? What is the parameter it is changing? See, there are the three parameters that can be changed: either the magnetic field, either the area, or either the theta angle. What is changing here? In all these examples, what is changing? In all this example, whatever I have taken, if you see what are the thing that is changing, it is change of magnetic field. In this example, what is changing? There is a change in area. You can see initially the area in the magnetic field is this much. Now it is this much. Now it is start decreasing. So here first the area is increasing. Here the area is increasing. Here the area is constant. Area is same. And here what is the happening? The area is decreasing. So here if the area is increasing, what is increasing? Magnetic field is increasing, correct? So what it will do, it will try to induce a current in such a manner that is the magnetic field will decrease because area will increase. So magnetic field, the reason where the magnetic field is more obviously. So it will try to induce a magnetic field in such a way that is the area will that is the flux will decrease. So it will keep like this and curl like this. Okay, in this case is the area is same, magnetic flux is not changing, so current is 0 here. Now in this case the area is decreasing, the magnetic field in the region will be decreased. It will try to induce a current in the such a direction that the magnetic field will be more, so it will put it the thumb and the curl like this. You will get the current like this, current like this. Clear? So this is the second case. This is the second case. Clear? Any doubt? Any doubt till here? So this is the variation of area we have seen. Okay. Next thing, some other examples. Yeah, we can take one more example. It is not about the calculation of direction of current, but you can take it. Suppose this is my coil and this is the magnet, okay, and it is falling from here. This is north and this is south. My question is whether A is less than G with the acceleration a. Okay, my question is a is less than g, a is greater than g, a is equal to g. What is the option? Which option will be correct? 1, 2, which option will be correct? A is less than g, a is greater than g, a is equal to g. If you understand this example, if you have understand this example, then you can easily tell me what is the answer for this. A is less than g, or a is greater than g, or a is equal to g, or you can say none of these also. Okay, if you want. See, when it will come down, what it will say, please don't come down. It will make north pole here, south pole here. This north pole will oppose each other. So when there is a oppose each other, so there will be one force in this direction, correct? So that means A is less than G. That is a correct option, because acceleration will reduce because of the repulsion, because they will repel each other, na? The acceleration will reduce. I can ask you one more thing here. I can ask this also. Suppose this is the same thing, and now what is happening? Now suppose in this case I am taking opposite. This is going upward. Okay. Now in this case you tell me A is less than G, A is greater than G, A is equal to G. What is the answer? Think like that. See, when it will go above, what it will say? When it will go above, what it will say? It will move, make south here, north here. Why? Because it will say, please don't go above, please don't go above. It will say like this. So in this case, my acceleration, A is less than G, or A is greater than G. So obviously A is less than G. Basically, if you try to understand, or sorry, mistake, I have make a wrong question. This is not the case. This is the case. It is going below here. Okay. So it is going below, so it will make south here, north here. So A is less than G. Basically, if you see, if you make any combination, it doesn't matter. It will always A is less than G. It can never be A greater than G, because G is the reason only due to which it is falling. Correct? Or it is going above, or it is going below. G is only the reason. Okay, G is only the reason. So it will try to reduce the G. That is only the Lenz law state, that current will induce in such a way that it will try to always oppose the reason by which it is generated. Okay, so similarly here also, if you see, the G is the only reason due to which the magnet is falling, or any other object, or a coil is falling. So it will try to decrease that G only. So in any one of the combination you will take, you will always get A is less than G. Clear? So I hope you have understand the complete idea about how to find the direction of a current by using the Lenz law. In the next session, we are going to discuss about the magnitude calculation. Till then, take care, goodbye, have a nice day.